Hello, my name is Joseph de Villemaret. I'm going to present you a novel approach for time series forecasting and its application to win a competition on the prediction of electricity load. First, let's talk about the setting of the competition. The objective was to design new forecasting methods after the break of March 2020 that we can observe here on the first graph. The framework was online in the sense that to predict day D, we had access to the data up to day D-1 at 8 a.m. Then another batch of data was released and we had to predict day D+1. To predict the load, we had access to meteorological forecasts, and we also used calendar variables as well as lags of the electricity load. We applied a few standard forecasting methods: autoregressive, linear regression, multi-layer perceptron, and also generalized additive models, which have been widely applied to the problem of forecasting the electricity load. As expected, these models trained on the data up to January the 1st, 2020 behaved poorly during the crisis. We observe a large bias, which quickly vanishes for the autoregressive, but lingers for the other models. Therefore, we consider a state space representation to adapt the model recursively. To apply the standard Kalman filter, we use a linear Gaussian state space model, where the different models yield different definition of the covariates xt. For autoregressive and linear regression, the definition is quite natural, but for the GAM, we freeze the nonlinear effects and we adapt a linear combination of these effects. And similarly, for the multi-layer perceptron, we freeze the deepest layers and we adapt the last one only. However, in this state space representation, we assume the variances sigma squared and q to be constant. That is, the model should evolve smoothly. Considering time varying variances could fit the data better, and we expect, for example, the evolution to be much faster during spring 2020 than before. That's why we introduce VIKING, or Variational Bayesian Variance Tracking. The idea of VIKING is to treat the variances as other latent variables in an augmented model. We also model their dynamics as random walks, but the variances must be non-negative, and thus we define them as exponential transform of these latent variables. The posterior distribution of theta t AT-BT is intractable. Therefore, we apply the variational Bayesian framework. The idea is to estimate the posterior distribution with a simpler factorized distribution, where the marginal of each latent variable is a Gaussian. And then the best factorized distribution is taken with respect to minimize the Kullback-Leibler divergence. As the minimum of the KL divergence doesn't admit a closed form solution, we use additional approximations. In the evolution of the Viking estimate of theta t, we observe that in the beginning of 2020, the evolution is indeed much slower than in spring 2020. We obtain improvements in performance due to our method, except for the autoregressive model, and that is quite understandable because autoregressive models are already very adaptive in a sense. The results in the leaderboard are a bit different because we combine all the methods presented to obtain a better final forecast. Thank you for your attention, and if you have any question or suggestion, please attend the poster session.